Welcome back, ladies and gentlemen. In this video, we're going to be looking at projectile motion. Obviously, you can see that. And we're going to start by looking at some definitions and trying to understand some basic concepts. But this is also going to require that you think back and recall information from Chapter 3. That was about accelerated motion. Chapter 2 had to deal with constant motion where acceleration was 0, and you'll need that as well, but that's quite easy. So to begin with, let's define what a projectile really is. So it's any object that is either shot or launched.
Francine DeWitt, please come up to the principal's office. Francine DeWitt, please come to the principal's office.
Pardon the announcements going on here in the classroom, and they're doing some announcements today. From time to time, you might even hear a bell ring in a few minutes here. But, so, any object that is shot or launched through the air. Now, that's a common way of saying it. It does not have to be through the air. It could be out in space, above Earth's atmosphere. It could still be a projectile. But quite commonly here in the atmosphere, and there's lots of examples, such as a jump shot in basketball, lots of others. It could be a frog as it leaps from one place to another. It could be a bullet fired from a gun. You can imagine almost anything, right? Now, there's something important about this that you really want to remember about projectiles. So after the projectile is launched, then the launching force does not exist anymore. That is really important. So for projectiles, the only force, or forces, let's cover all the bases here. The only forces acting on projectiles are gravity and drag, air resistance, right? And with this guy, drag, we will usually be ignoring it. And there's a couple reasons. Number one, it makes our problems easier, because if you are trying to figure out drag and incorporate that, the problem actually, if you really do it right, is super complicated, and we're not going to get into that. But also, lots of things moving through the air, they move in a way where drag really isn't affecting the motion of the object in a big way. Something like a feather falling, sure. Something that is spending a long time falling through the air, yes. Drag is a factor. Something moving at terminal velocity, of course. Drag is a factor there too. But for these problems, you know, the jump shot, the frog hopping through the air, even, there's the bell. Even a bullet fired from a gun. For our purposes, we're going to ignore drag and not have to worry about it, unless a problem or situation indicates otherwise. So this guy is important, and really there are no other forces that are important for us, and that matters. So that when you do a jump shot in basketball, of course your hand is pushing the ball during the shot, during the creation of the shot. But once it leaves your hand, you're no longer touching it. You're no longer applying that force to the ball. And gravity will be the only force affecting its motion. It already has motion, it's already moving. But that force of gravity will change things a little bit. You'll see that and how that works. So there's another term. Projectile is one definition you want to know. And another one here is trajectory. That's supposed to be A, sorry. Trajectory. And this is simply the path that a projectile follows. Now, the interesting thing about this is that if we're ignoring drag, and that's what we're doing, then all trajectories of all projectiles, are parabolic. Now, parabola is, it's, I don't know, you might think of it as a U-shaped kind of thing. It's not really like a U. It never goes truly vertical. But if you imagine this, you know, you launch it, a jump shot, or you toss a ball to somebody, and it kind of goes up and down. There's this curvy nature to it, right? And sometimes it's launched mostly straight up, and then comes back down. It's still parabolic. There really is no straight part of the pathway. Okay, a couple good definitions there. Regarding gravity being the only force that acts on projectiles, ignoring your resistance, then I got a question for you. And the question is this: so, this projectile is moving. Any projectile, well, it's moving through the air. Okay, it's going. We launch it, right? Up and down. Okay. Well, it's moving in the x direction and it's moving in the y direction at the same time, right? But we know something about gravity. Gravity only acts straight down, right? Well, maybe, I'll just write G for now, for gravity. Gravity is only acting straight down. Will gravity affect the horizontal part of this motion? And the answer is no. Gravity will affect the vertical part. Yes. And this is going to be real important for us to keep in mind. We'll see that in just a moment. I want you to imagine something. We're going to stand at the top of a cliff. Okay? And at the top of the cliff is the soccer ball. And we're up here and we're going to kick the soccer ball horizontally. But right before you kick the ball, gravity breaks. And you give the ball an initial horizontal velocity. So there's a velocity in the x direction. And there is no gravity. Gravity broke right before he kicked it. So what's going to happen? Where will the ball go? What will be its trajectory? Well, its trajectory will simply be a straight line, right? It will keep going in this direction forever until it bumps into something or gravity gets fixed, right? So we can see that. And what we know about this is, well, it's going to keep doing what it's already doing. So if we were to make a motion diagram, it's going to start here, and let's say 1 second later it's there, and 1 second later it's going to be there, and 1 second later it's going to be there. And the spacing of these dots really is important, right? You guys recall this is from a while ago, but there's a reason for learning it. It's when you get to analyze projectiles, cool stuff flying through the air. So the deal is this: the spacing is equal, the velocity is constant and unchanging, right? So what is our acceleration in the x direction? It is 0. Okay. Now I want you to imagine just a slightly different situation. We're at the top of the same cliff, right? But instead of kicking the soccer ball, this is separated. Instead of kicking the soccer ball, I'm going to drop it off the cliff. And we're not going to push it, we're not going to throw it or anything, we're just going to let go. So we are going to have an initial velocity in the y direction. So initial in the y direction will be 0. That's what dropping it really does, really means. And now here's the thing. We're going to track this after as time goes on, and it's going to eventually fall to the bottom, to the base of the cliff. After 1 second, well, let's see, we're going to start right there. After 1 second, it hasn't gone very far, maybe there. After 2 seconds, it will have gone a little further. After 3, a little further. After 4, and at let's say it lands right there. Maybe it does, maybe it doesn't. It depends on how high the cliff is, right? But what's going on here? We see a small velocity, little tiny velocity there, and then velocity was larger, In the third second, velocity was even larger, and even larger, and even larger. So we're seeing velocity change. It's speeding up. Well, duh, gravity's pulling it down and accelerating it. So we have an acceleration in the y direction equal to g, and we're going to consider that to be in the negative direction. So that's going to be and we know the value, negative 9.8 meters per second squared, right? Okay, now the interesting thing is going to occur when we actually look at these two things happening simultaneously at the same time. It's going to be helpful sorry about that, patient with me, appreciate that. It's going to be helpful to have some graph paper just so the spacing can look good and make some sense easily. So I'm going to redraw the cliff. About there. All right, so what we said was if we kick the ball and there is no gravity, then every second it's going to go the same distance. And that would be constant velocity, right? We also said that in the other situation, if we just drop it, well, every second it's going to fall, and it's going to fall by different amounts each second. So it's going to go there maybe, and then maybe it's going to go here, and then a little further, and then a little further, and then a little further there. And here's the kicker. Here's what we get to notice about this. All right, I'm going to have to pick a different color here so it stands out a bit. And so what's the result? Well, in real life, gravity doesn't break, and so we can't kick it off the cliff and have it do this. And in real life, we're going to do more than just drop something because we're bored. You know, if we actually do kick it off the cliff and gravity works, then what do we see that happens? We're going to see, do it this way here, we're going to see that in 1 second of time, the ball would actually be here. It has moved horizontally by a certain distance, and it has moved vertically down by a certain distance in 1 second. In 2 seconds, we're going to see the ball be here. Now you'll notice it's gone the same distance horizontally, right there, but it's gone a little bit more vertically, about 3 seconds. In 3 seconds time, that's going to go and end up here. And 4 seconds. This is not something, this way of sort of drawing things, this is not something you do every time, don't worry. But it's helpful in explaining this stuff initially. So then, right before it hits, it's here. I'll come down that one and meet it. Okay, make sure I'm on the right line, right there. So the interesting thing that you want to see, the reason for doing this visually is both the horizontal motion and the vertical motion are happening at the same time. And they combine to produce this curved pathway that the ball will follow. And eventually, yes, it's going to land some distance away from the cliff. It will have spent some amount of time in the air, and we get that. Now, what is this shape? This shape happens to be a parabola. It really is. It's not a full parabola. It's actually half of one. You would for a full parabola, you'd have to mirror this going the other direction and down, but that's fine. So you want to recognize that shape, and remember this path is called a trajectory, right? The trajectory has the shape of a parabola. Now, that's sort of what I want you to see, that the horizontal motion is constant in the x direction. We have constant motion. And in the y direction, we have accelerated motion. Right? So how does this work? How do we figure out, where the ball would be, and maybe some other things? We have to solve this kind of problem by dealing with the vertical motion and the horizontal motion separately from each other. And that gets us to these sort of problem-solving tips that I want to go through with you right now. So, tips for problem solving, or solving problems, solving projectile motion problems. All right. These are also in your textbook in 6.1. Please take the time to read through these. The wording is a little different, but it's essentially the same thing that I'll be saying here. So, number one rule: the horizontal and vertical motions are separate. And must be dealt with separately. I mean, it's really that simple. And that's going to make your life a lot easier. That one right there. Without doing it this way, it's just not going to work out for you. So in a few minutes, I'll show you what that's going to look like. The next tip: the vertical motion is really identical to dropping something. Remember, we looked at this. So it really is identical to dropping something, or to throwing it straight up, or even throwing it straight down. So the vertical part, the vertical motion, is identical to dropped objects or objects thrown. Straight up or down. And that's it. So you would have a rate of acceleration after throwing it. The rate of acceleration would be 9.8 in the downward direction. You might have an initial velocity of 0 or some other value. But it really is kind of straightforward. It's the same kind of problem you solved a whole bunch of in Chapter 3. The next tip number 3 here: the horizontal motion is constant velocity. I'll just write constant. Horizontal motion is constant. In other words, acceleration in the horizontal direction is 0, right? Well, if I'm going to say this about the horizontal acceleration, well, what's the acceleration in the vertical direction? Acceleration in the y direction? Well, that's going to be equal to g, right? Except it's in the downward direction. So we'll see negative g, and we'll say that's equal to negative 9.8 meters per second squared. Right? So that's your vertical acceleration and your horizontal acceleration. The final tip is that horizontal and vertical motions are linked or connected by the variable of time. So in other words, from launch to landing, it just takes a certain amount of time, and that time is the amount of time it takes to travel horizontally, along with the time it takes to travel vertically. So there's a horizontal, and then there's also an up and a down vertical, right? If you can imagine that here. So there's a time it takes to get to landing from launch, and there's also a time it takes to go up to the highest point and then back down from the highest point, right? Well, the time it takes to do this guy is the same amount of time as it takes to do that. And so time is the variable that links your horizontal and vertical together. It's the connection, and that connection is very useful. So, to wrap this up, I want to go through an example with you guys. And it's excuse me, get my tongue working. Here we go. In this example, there's a ball. On a cliff. I swear I do speak English. And we're going to kick it off on a cliff. The cliff is 4 meters high. The ball on the cliff, 4 meters high, is kicked horizontally. With an initial speed of, let's give it 11 meters per second. Okay. So the question that we're going to answer this time around is going to be, well, how far from the base of the cliff will it land? How far from the cliff will the ball land? Okay. So part of this is getting back to basic problem-solving strategies. I have a situation basically presented as a word problem. I need to sketch this out. So, real simple. Nothing special here. Just do one of these guys. And imagine, even if you can't quite draw it accurately, imagine it's going to be a parabolic trajectory, right? It is kicked horizontally. There's your initial velocity. And there is some distance where it will land from the cliff. There's some things that are important here, and this is going to be more notation than we used to do in Chapter 3, because this distance is horizontal, so I'm going to put dx. That's a subscript. For those of you guys in advanced math, particularly the calculus, you're going to see dx's all over the place. This is not the same thing. That's a subscript x. Here, there is a vertical distance, and that's going to be dy. This velocity happens to be in the x direction initially. And so, and I know that because it is kicked horizontally. There is no vertical part of this kick. So 11 meters per second is Vx. Well, what is Vy? Well, what this means is, it's not said, but it's implied that Vy is 0. But that is the initial vertical velocity, right? Because after it starts to fall, it's going to have some vertical velocity. So this is also an initial horizontal velocity, right? Well, the thing about this is the horizontal acceleration is 0. So my final velocity, or this horizontal velocity, will remain constant the whole way until it lands. The velocity as it goes to the side remains at constant speed. But my acceleration in the y direction, remember gravity, negative g, so negative 9.8 meters per second squared. There's some important facts to keep in mind. Now I know one other number, and it is this value. The cliff is 4 meters high. Okay. And the question ultimately is looking for that guy. That's what I want to know. Now you might say to yourself, well, okay, brilliant. I have a speed, I have a distance, I should be able to find a time. But go back to those tips for problem solving. I have to treat the horizontal and vertical separately. And the vertical motion is accelerated motion, the horizontal motion is constant. So I can't mix things up. I cannot use a horizontal velocity and mix it up with a vertical distance and expect to get an answer that is meaningful. It will not. So here's the trick. Here's what I know. If I have a number here